Hello. Welcome. Bienvenidos. Welcome to our second highlight lecture. Today is going to be Venus. Venus, of course, is an interesting planet from a scientific point of view, as you will hear today. But I also wanted to put a little bit this talk in perspective of what we're doing here. Venus for me is an example of how to work scientists and engineers together with a specific goal. It has been the latest ESA mission in solar system exploration, just launched it last year and inserted in orbit beginning this year. But also the record for time to develop a mission in ESA. It was done fast, decided, developed, launched, and we are now getting the size. This working together is something that Venus Express is showing us. Then, of course, now that we are there, we are trying to understand Venus, the atmosphere, though of course some information we are getting about what is below the atmosphere of Venus, but the main object that we want to analyze is its atmosphere, evolution, and so on. And this is not only for the purpose of our own knowledge as astronomers or planetary scientists to understand one object of the solar system. It's also to extract lessons about our own atmosphere on this planet, in Earth, greenhouse effect, and many other areas. By understanding an extreme case like Venus, we're going to understand more the physics of our own planet. So for me, it's also an example, this mission, of how to bring space closer to people. And tonight, for this lecture, we have as a speaker Dr. Gerhard Schwehm. Dr. Schwehm got his PhD in applied physics, but very soon he joined ESA. Actually, after working a little bit at ESA, he moved to ESTEC. He joined in the agency with our first solar system mission, actually unique solar system mission in ESA for many years, which was Giotto, a mission to Comet Halley, as you may remember. And he worked in that mission until we started thinking Giotto was so great we had to do something even better next time, and then we started what is now called Rosetta, at that time called as Comet Sample Return Mission. But Rosetta, now in orbit, launched in 2004 and in its way to Comet Churyumov-Gerasimenko, is his mission, and he is still the project scientist of that mission until we get to the comet, I guess, after 10 years of navigation, so he will enjoy when we get there. But he got involved in many other aspects in the planetary activities of ESA, and then was the head of the planetary missions division at that time. And then when we created the division for operations, science operations of solar system missions, he became the head of that division. So that then, as taking the responsibility of all missions in orbit in the solar system, he is the king of the solar system of ESA, including Venus Express, of course, which is already delivering the science and in orbit around the planet. So that he will tell us about the latest results, scientific results of that mission. Before giving him the floor, I just wanted also to remind you that you may have seen close to the entrance of each row a paper which is an audience evaluation paper. Please remember to fill this in at the end of the talk, I guess, and then put it back outside this room. There are tables with some boxes. Put this paper and those boxes in on the table, because this is good for, of course, the organization of these lectures. So now, without any further comment, I just want to give the floor to Gerhard Schwehm.
Thank you, Alvaro, for this nice introduction, and it's an honor for me and a pleasure to introduce Venus Express to you today here in Spain. Not only that my boss is from Spain, but also Spain plays a very important role in the Venus Express mission. As some of you might know, the designated ground station for Venus Express is Cebreros, just outside of Madrid. And in spring next year, we will also move the science operations to Madrid, to ESA's European Space Astronomy Center. So basically, Spain will become the heart of all the data that will be downlinked to Earth, and then go to the scientists, and we will also work on the data in ESA, and finally we'll have the archive of the Venus Express data that will be then available to all of you in Spain. So Spain is really an important player in this, and as Alvaro already said, and I put it down here, it's not my mission in the sense. I have the pleasure to introduce it to you, but it's really a team effort, and it's the science working team with all the principal investigators, the interdisciplinary scientists, it's the Science Operations Center, and last but not least, the Mission Operations Center in Darmstadt, and they all contribute to this very successful mission. I hope I can give you a little bit of an introduction on this mission and also show you that it's a success. Venus is one of the most famous planets, so to say. It's the morning star or even the evening star, and I believe everybody has seen Venus when traveling in a country like this where you have clear skies, or in South America, but it's really an impressive planet, and it's also something that you can tell your kids very early on. Venus, named after the goddess of love and beauty, is also a subject of a lot of paintings, sculptures in science, and you will see that it comes again. Venus is one, so to say, of the very famous figures in the mythology and also in planets. And for us in space research, Venus, as it's close to Earth and it's nearly the same size, as you will see, it's also one object you need if you want to get to the outer solar system. Because of its size, it's really the target for gravity assist, because it's big enough and you gain a lot of orbital energy when you fly by there. I will subdivide my talk in introduction, give you a little bit of background history of Venus exploration, the science objectives of the mission. I will show a little movie on the mission scenario and show the science payload, and then I come to the first results. And we have been for half a year in Venus orbit, but already got a lot of results. Some of the stuff is really new, just was shown for the first time 2 weeks ago, and will be published later this year as it's planned now in Nature. Venus was the planet like Mars today, where all of the interest concentrated on in the 60s and 70s, and there were a lot of missions that went to Venus, and as you see from these lists, and I don't go through it, there were a lot of losses there. It was the early days of planetary exploration, and you paid the tribute due, so to say, to these complex undertakings. But we have also a lot of very successful missions to Venus, and you see there's a whole lot, all US, USSR, and we already learned a lot about Venus. And we already had a successful landing on the surface of Venus, Venera 9, 22nd of October 1975. So basically 30 years ago, and at that time we got information about the atmosphere, also a little bit on the surface structure, atmospheric gradients, and then the composition of the atmosphere. All information that really showed a lot of new things for the scientists, and that helped us to improve our models of Venus. But still, there were a lot of unknowns. And here, this is the last successful list, and you see that what was basically the real dedicated mission to Venus was in '89 Magellan an orbiter. It was a radar surface mapping, very successful, that gave us really a map of the Venus surface. And then it was quiet for quite some time, and only we had these flybys by Galileo and Cassini when they were on their way out, Galileo to Jupiter and Cassini to the Saturn system. They needed Venus to get their orbital energy. And still a lot of questions were open, and that is really the driving force behind the decision in the end for ESA to go to Venus. It has, in the scenario where, and as Alvaro said, it was one of the missions that we could do fairly cheaply, very fast, because it is based on the developments we did for the cornerstone mission, Rosetta, Mars Express. It's basically a family, and you benefit from these developments. And it really fits very well in the whole sequence of Venus exploration. We ended up, as I said, in 89-90 with a radar mapping of the surface, and still a lot of these questions about the atmosphere were unsolved. And therefore, in a call of mission ideas, the proposal was submitted by the science community, and that one should reuse Mars Express, and then really go into a Venus orbit with a mission dedicated to the atmosphere. If we look in the context why we are doing it, it's basically ESA has also a mission to Mars. We have a mission to Venus, and as Alvaro said in his introduction, is basically what we do is comparative planetology. We want to study, so to say, our twins, Mars, another extreme, and Venus, to understand our Earth. And we have just listed a few things, but what we see here, Earth is unique, not only that it's perhaps the only planet where life exists, but also, and perhaps it's due that we have plate tectonics on Earth and volcanism. But that's one thing we want to find in Venus, if there has been or is there active volcanism on Venus. We have water oceans here that we don't see on Mars today, we don't have on Venus, and we really have to understand the composition and the development of the atmospheres, both of Mars and both of Venus, to understand why the Earth has an atmosphere that was shaped as we see it today. And this is one of the reasons why we do these missions. We have Vex and Max again in the art history. You also have by Botticelli painting of Venus and Mars. And these are, so to say, the twin missions that help us to understand, or should help us to understand, the evolution of the Earth. If we look in both missions, and just to give you an introduction, what is the difference between these two missions? What we want to do on Mars is basically the global coverage of the planet. We want to see what the ages on Mars are, shaped by volcanism or glaciers. Where did the water go? We do on Mars radar subsurface sounding, and we look into atmospheric escape processes. This is one of the clues that's becoming more and more important to understand how atmosphere works, is the interaction of an atmosphere with a solar wind, how the solar wind shapes the atmosphere, how it, so to say, penetrates deep in the atmosphere and takes some of the molecules, some of the particles or components out of this atmosphere. We know it from Mars, have observed it with one instrument. We have also on Venus Express. We even saw it with Huygens at Titan. So there are some of these processes that are very important to understand how atmospheres shape. For Venus Express, the prime objective is really the long-term mapping in the UV, from the UV to the thermal infrared, and to get atmosphere temperature profile and to understand the dynamics of the atmosphere. Just a little comparison. Venus is just slightly smaller than Earth. There's 20% less mass than Earth, and also the gravity is only 10% less than on Earth. So it's very similar to our planet, but both planets, as we know, have developed totally differently. Venus, and therefore I selected this title, and I was just told that has been used 30 years ago or 20 years ago for another talk from Magellan. unveiling the secret, because what we can't do in Venus is we can't look at the surface easily. We had to use Magellan to map the surface with radar, but we have this cloud layer at around between 50 and 60 kilometers, a really thick cloud deck, which basically prevents us to look down onto the surface. But also, there are a lot of other riddles in these planets. It's first of all to see how this atmosphere works. And if we go to the Earth and Venus, we see the wind system we have on the Earth. It's fairly well understood, and it's one of the tasks that our atmospheric physicists tackle, and they have a lot of data from Earth observing satellites. We have ground truth and all this stuff. We understand fairly well the system on Earth. On Venus, we have something that's called superrotation. The atmosphere rotates much faster than the planet, the Venus itself rotates, and we have to see how this, so to say, weather system is driven. We have, as I already mentioned, planets of basically the same size, but surface environments, they are totally different, because, okay, the pressure on Venus is much, much higher than on Earth. Temperatures are 500 Kelvin, and it's really a totally different system that drives the atmospheric dynamics. And one wants to find out and study how this system works, and as was mentioned, greenhouse effect. Venus is one of the worst examples you can imagine of a greenhouse. We are glad that we will never get closer than Earth. Whatever we try to do to our atmosphere, we can be sure it will not be as bad as on Venus. But it just shows what happens if you drive a system to the extreme. And this is basically a picture which I got courtesy of my colleagues from JAXA, who planned the Planet C mission that should be launched to Venus in 2010, and they also concentrate on the atmosphere. This is the hierarchy of Earth's meteorology, where we know basically all these steps as a, so to say, function of scale, as a function of time, and we have to understand the micro, meso, and macro effects on our atmospheric dynamics. On Venus, that's what we know today. You see all these big question marks. The only thing we know is that this is a system with superrotation, and what we want to find out now slowly is that we can put in values where all these question marks are. And this is one of the objectives of the mission. The other objective, and I already mentioned it, are these escape processes. What molecules are escaping the atmosphere? How are they taken out of it by the interaction with the solar wind, and also possible evolution of the water on this planet. Another question is, what are the origins of the highly radar reflecting areas on the surface that were seen by Magellan, and the question if there is presently volcanic or seismic activity on the planet. As it was mentioned, it's a reuse of Mars Express. Here, just two images of the spacecraft. On the left, you have Mars Express, right? It's Venus Express. There were only minor modifications necessary, at least the most importantly, that was driven that we are going much closer to the Sun, to point 7 AU, that's the thermal design, and you see that Mars Express is nicely packed in black, and the other one in our golden thermal foil just show that we are in different thermal regimes. We needed obviously smaller solar arrays because we are much closer to the Sun, and a decision that was taken by the project where the scientists were not so happy with, because we are much closer to Earth. We also could use a much smaller high gain antenna. And the scientists obviously would have liked to keep the same as on Mars Express, because that would have increased the data downlink. And we tried, as we had only a short development time, tried to use an existing scientific payload. So what we were looking for were spare units from Mars Express and from Rosetta, just cannibalizing the EQMs we had to really accelerate the development time and to save cost. And these are the instruments we are having on Venus Express. There is Aspera, the analyzer of space plasma and energetic ions from Sweden. This is the instrument that comes from Mars Express. We have a magnetometer, which is basically an instrument that was added because we don't have a magnetometer on Mars Express. We have the planetary Fourier spectrometer from Mars Express. SPICAF-SWA, it's Mars Express with a added infrared channel. We have Venus radio science, which is the instrument that was copied from Rosetta with another PI, but it's the same group. Then we have VIRTIS, which is the Rosetta spare, the UV visual infrared mapping spectrometer. Now also under a different PI ship shared between Paris and Rome, and this was on Rosetta instrument that was coming from our Italian colleagues. And then another new instrument that was added is the Venus monitoring camera, a new development of a small camera from the Max Planck Institute for Solar System Research from Lindau, and a group that has a very good track record on camera development starting from Giotto, and they have a camera on Rosetta and are involved in a lot of other instruments. This is what we have on the spacecraft. We have a fixed high gain antenna, and we'll come to this, and all instruments on the spacecraft are body mounted. So we have to point the spacecraft with one side to Venus, take the data and the images, then turn the spacecraft and downlink the data. Here you see the instruments field of view. They are all co-aligned, and you see that they all fit into the big field of view of the camera. And the camera also has a field of view that we can basically get the full Venus into the aperture. Here, the spectral characteristic of all these instruments, you see that they are nicely overlapped, which turned out to also be very good that it was designed like this, because the only instrument that doesn't work, and I put in brackets yet, is the planetary Fourier spectrometer, an instrument that we inherited from the Mars Express mission. This instrument is the only instrument where we still have to try to get it working. But with the wavelength selection, you see that we have a very nice overlap, and that we, so to say, can compensate for the loss of, or potential loss of this one instrument. For surface study, what we can do bistatic sounding, some kind of, with the radio science, so to get images of some kind of images of the surface. We can go down with VIRTIS in the 1 micrometer range down to the surface, because there we have a window in the atmosphere, and we can search for active volcanism. And with the spectrometers, we get the composition of the lower atmosphere, and there's also hope that we could search for Venus quakes. And here is just how important these plasma and escape plasma environment studies and the escape processes are. This is really to study the solar wind atmosphere interaction, and we see here below, we see an image from an energetic particle images from Mars. You see how some of the molecules are there released and escape the Martian atmosphere. And this is also measured by the same, these are identical instruments that we have on Mars Express and on Venus Express. Just briefly, the mission timeline. The Venus Express was launched 9 November 2005 from Baikonur, arrived at Venus 11th of April, was injected then in the Venus orbit. After the commissioning, the normal operation started 2006 in June, so that just, as I said, we are basically half a year now active there, and the nominal mission will end in September 2009, but the spacecraft and all the instruments are in such a wonderful health that we are sure that we can extend the mission, and we will go for mission extension. That means that we get the funding, that we can really go on at least till December 2009. This is the orbit, and there just what I mentioned, that we have to turn the spacecraft so that we take data when we are close to Venus, and then we turn the spacecraft, and then we have about 10 hours, 8 hours to downlink the data to separators. It's a 24-hour orbit. It's always the 8 hours to work, and that's also good for our operations people that they don't have night shifts. It's always the same 8 hours when the data come down, and they all come down to ground here in separators, and we have a very, so to say, efficient system where we really get most of the data return that we need. This is the mission profile. I just show you now that you can rest a little bit and I can rest a little bit. The movie of the launch and how the whole sequence went. This was the launch from Baikonur. It was a Soyuz fregat, and this is the fourth stage, the fregat upper stage, that was then injecting Venus Express onto the trajectory to Venus. So here you see the spacecraft as it's on its way to Venus, and then on the 11th of April it was captured by Venus, and this is another scene where it goes back to Botticelli. That's from the movie Münchhausen. This is Uma Thurman, and that's like, I think the scientists or some of our operations people looked on the 11th of April when everything worked, and the guy looks like Manfred, you know, for insiders, and I thought they would probably. But this is, you see that this thing is taken up in a lot of. This is when we got there to Venus, the final maneuver, and we were in orbit. And then it took a couple of days to really get it down to the final orbit, and this was, and I have to mention it here, wonderful work of our team in ESA Flight Dynamics and the mission operations team. And I could have shown, instead of Uma Thurman, there's the same scene that goes back to Botticelli. There's, for those guys who know James Bond movies, and with Dr. No, there's Ursula Andress coming out of the sea. It's with the same theme. I could have shown that as well. But I think what I show you now is the first images. And this was one of the sensational things I would say we got, that within a few hours from the orbit insertion, and this is from the first orbit, we got this great images back from the Virtus instrument. And just with these images, one could already say it was worthwhile all the effort to get Venus Express there, because this shows already, the first images, what promising science we could do. And you see here the very prominently, and I don't know if you can dim the lights here or get the lights down there, this polar dipole, which I will show in a few more images, and because this is really one thing that was predicted, was known from Pioneer, but it was clearly shown already in the first images. And with what we do with the Virtus spectrometer, this has a very wide wavelength range. It goes from 1 micrometer to 5 micrometers. You're basically building up image cubes. You go from 1.27 to 2.4 micrometers. That's where you basically can look through the atmosphere, deep into the atmosphere, and you're building up these images. It's a very rich, so to say, way. And this shows the first, so to say, composite of observations done by Virtus in the infrared at 1.7 micron during the Venus orbit insertion, and this shows when looking in the atmosphere already, it was, at least for guys who work on atmospheric sciences, it was, they all said wonderful stuff, and it's quite clear what you see here. This is the Hadley cells that I showed in one of the images before, and this is basically what we have on Earth, and you see there's in the middle, this Hadley cell is basically that you have a similar structure as in the atmosphere with different areas of dynamics as we see it on Earth, but we have to understand it, we have to study it, but it shows from the images we get, we see all these wonderful structures, differences, and I think this is a sign that our dear colleagues in atmospheric physics have to work a lot to understand it, but they also get now a very rich material where they can work on. I go through a few of the results. This is from the Aspera, where I said that they look into the plasma environment and in, so to say, the atmospheric loss processes. This is basically shows in the top level the orbits, and then some of the spectra that have been shown just shows that Aspera and the magnetometer also work quite well, and you see if you look in the spectra in the different, for the different atoms and molecules, to see where we, so to say, have most of the material and which material is getting off there. So this is just the beginning. As I said, these data are fairly new, and you have to see that the teams, after they have calibrated their instruments in flight, have to really work on analyzing the data. Now, if we look for from the SPEAKAF instrument that use stellar occultations to sound into the atmosphere, I just show 3 examples, and this is the altitude when we look down in the atmosphere, and also shows the CO2 column density. So we see already a very nice profile for the CO2. Here we have the density derived as a function of the altitude above the Venus surface, and here you see the dust optical thickness as derived from stellar occultation. You see that you have also a peak there close to where the cloud layer is. So these are, as I said, preliminary information, and then you can also compare the CO2 densities from different orbits, and you see that there is a very, so to say, good, they fit all fairly good together, and also a sign that this instrument works pretty well, and most of the initial measurements were really done to check the performance of the instrument. And another thing here is with the radio science instrument to derive electron density profile as a function of the height above Venus surface. If we go on, we have also done performed the first biostatic radar measurements. That means that we turn the antenna onto Venus, and so to say, measure then at the Earth the reflected radiation, and that gives us, so to say, some kind of radar imaging of the surface. This would take, I think, another half an hour, and the PI has shown me these results a couple of weeks ago, and we were discussing them for 3/4 of an hour. So I don't want to go in much detail, but it just shows that this works, that we have done by static radar imaging during the commissioning, and that we have a tool there that can be used during the mission. And this is just to see, there it comes, yeah. Just to see some of the structures on the surface that was used, and to really correlate some of the measurements with surface features. As I said, very preliminary. Here is the first movie that was put together for the VMC, for the camera. This is from the first perisender pass in the UV filter. It's not very impressive, but you see the structure in the atmosphere, so you can we can build up movies. The camera had to be calibrated, as some of you might have heard that they had some a stray light problem, but also the camera was exposed to sunlight during some phase of the mission, and that was not a fault of the agency or of the PI, but the company that had built the detectors just didn't tell them that they should not expose them too long to solar radiation. But this could have been corrected, and the result is, so to say, the first movie of the atmosphere while I'm flying over, but there will be much more to come. But the STAR instrument, and I will close my talk with some of the results again from VIRTIS, is up to date, is the visual infrared mapping spectrometer, because with this instrument right from day one, basically we could get exciting results. Here is from the orbit insertion maneuvers, and you saw the Venus clouds on top at the night side at 1.7 microns, and on the below it's at 380 nanometers. So in the UVs you see the different images, and you could from that you could derive from the cloud features, you could also derive wind speeds and wind shear. This was done, and this is from one of the early measurements, and one can compare that with the Galileo measurements from February 1991, and ours are from April 2006. So you see it's they are to some extent very well comparable, but there is a lot of work has to go in there to really analyze the data in detail. One of the things that was predicted and seen was this vertex at the South Pole, you know, this with the inverse S shape that was found immediately, and here an image in 5 micrometer range. Here is the old observation from Pioneer Venus, 1980, from Fred Taylor, one of the leading scientists in the Venus Express mission, and this was at 15 micron. And here you see it in the close-up of this dipole. That's about at the height of the cloud level, at the top of the clouds, and you see this very well, but the big surprise was that you see this also below the clouds, when you can penetrate the cloud deck at 1.7 micrometers, so you really can look through, and you see that you have this feature also below and the cloud deck, so that it's persistent and goes through there, and it's also slightly shifted away from the South Pole, but it really goes deep into the atmosphere. This is at a later orbit, again in 5 micron, and then you see here, and this is one of the powers of this instrument, and this just shows you how it goes through, you know, down to 20 kilometers. Yeah, so from the top level, you can basically, in the different wavelength range, you really can look down to 20 kilometers, and you can follow these atmospheric features, and I think that just demonstrates the power of that instrument, and also demonstrates what we can expect from Venus Express. With all this data we get, I think we will make a big step in understanding the atmosphere of this planet. The dipole, and that is one of the first results, is a region of very high thermal contrast, and that's also what the scientists claim, the details you see in these images, and they look, what you get a full spectrum here, and if you look in this spectrum, you see that you get the thermal brightness differently at different depths, that means at different height above the surface, and this explains a little bit or is a background for understanding this feature. But one thing we also wanted to demonstrate with Venus Express, that we have a chance to really look down to the surface, and this has in the meantime, I believe, has been demonstrated, and these are some of the first results, that you with Venus Express, that we have the chance to really look deep down and reach down to the surface. This is a comparison with the synthetic radiance image, so to say, based on Magellan topography that is artificially produced. And on the left-hand side, you see the first data after orbit insertion at 1.02 micrometers. This atmospheric window where you can go down, and you see that these synthetic, so to say, features are very well represented in the actual measurements. And this is also can also be linked very easily to some of the regions on the Venus surface. If you look at another picture, and if you look at the resolution which we had already in the capture orbit of about 200 kilometers, it's if you, with this, so to say, confidence that you can link these features that you measure to surface features, they have resolved some of the structures and they just linked it to some of the features that we know from the Venus surface map, from the globe you have that was built up based on Magellan data, and there we see very nicely how this is linked to actual surface feature, and I think this is another great tool for future studies. And the last images I want to show is basically the correlation to ground, where you have some of the ground images, so to say, from Magellan, and how they come together with images that are taken, have been taken with VIRTIS in the different wavelength range from 1.02 to 1.05, 1.27, and okay, with a little bit of fantasy, but I think there's a lot of work goes in, but it's quite clear that we can relate this to surface features on the planet, and that we have, as I said, a wonderful tool also to study the surface. You know, there's those who are from Germany, they might have learned the lead from von der Glocke, and there's this famous phrase in there that we had to learn it by heart. When this says, with the bridal dress, the veil, the beautiful illusion is torn, the passion flees, love must endure. But I can assure you we have only lifted the veil a little bit. The passion is still there with the scientists. They are eager to get much more data. We know that the community wants to go to Venus again with another mission, even if we have just started with Venus Express. Our Japanese colleagues will go in 2010. Our American colleagues are discussing with us missions where we put balloons in the Venus atmosphere to learn much, much more. We have just started to unveil the secrets, and it's not like in Botticelli's image, it's more in the painting, in a modern version, which is perhaps also a version that you can show in the US, which is Marilyn Monroe, and we have just started to learn about, and I think I could give you a little bit of the excitement we have about this mission, the potential this mission has for the future, and I'm quite sure you will learn much more about Venus Express and about scientific exciting results. Thank you very much.
Okay, I want now to open this lecture for questions. If you have any question to make to Gerhard, just to remind you, please raise your hand if you want to make a questions, but then identify yourself. And then for question, you will see there are microphones around on the table. So you can use this microphone by pressing the button. I have, of course, a master button, so I can shut you down, so that not everybody's going to talk at the same time.
Does this work? Yeah. You mentioned there were problems with the planetary Fourier spectrometer on Venus Express. What's the current situation with that, and how do the other instruments help to recover the data that's lost?
Now, what we do, with all the instruments, we collect the data, and as you saw, there's overlap in the wavelength ranges we get, not perhaps in the resolution. So what we try to do is getting basically what the Fourier transform, the PFS would have given us was temperature profiles and also composition profiles in the atmosphere, and that we try to recover with the other instruments. So the PFS, we still try to solve the problem with it, but might not help. But in the end, we have basically the same wavelength coverage, and we have also the similar resolution of the atmosphere with other instruments, and there we try, so to say, to do the science. It's not that we can recover the same data, but we can recover the science.
You showed us so wonderful pictures from Venus, not only from the planet, also the the drawings. And nevertheless, it seems very unlikely that there is really life on Mars. My question is, did you do any precautions of planetary protection, or did you assume that Venus is a lifeless planet?
We assumed what the COSPA regulations or the COSPA recommendations gave us, that we have not to do anything, that Venus right now is a category that we don't expect to find life there. And I know that there's at least one group in the world, in Seattle, they believe there might be in the upper atmosphere, there might be a chance that you have, I don't know if you say prebiotic molecules or what, you are the expert in this one, but they say this, but as we are not intending to go into Venus basically right now, but we are not penetrating it right now, and we have no lander on this, so we just went that this is a normal mission and there are no special precautions to be taken. But that might perhaps change if we learn more, so you know how these things go.
Okay, any other questions? And please identify yourself. Last one was Gerda Herneck, but this one is over there. Yes.
Good afternoon. My name is Yunir. I'm a student from Germany. I had a question about, as far as I know, the Soviet Union had some technology for observation of this planet. Did you consider that technology as well?
No, for this mission we didn't consider that technology. As I said, this mission was designed to build an orbiter and to concentrate on atmospheric studies and basically use the technology and the instruments we have available. In the studies we do for future exploration of Venus, which is more or less there's a Venus Exploration Assessment Group in the US, where a lot of Europeans participate, as we have a lot of US scientists in our mission. If you look in technology that you would need to put something down on Venus, there you are going back, in some of the discussions you have, back to the Soviet technology, because there you need something very robust that can stay for quite some time, or for some time on the surface. But these are things that are being discussed, but for this mission it was quite clear that we had to go with the technology we had available and develop for Rosetta and Mars Express. But we have also a lot of Russian scientists here on this one, and one of the key scientists we have is Titov, and he was involved in the Russian program, so we have very close links to the Russians. He's now in Lindau, and he's one of the key scientists, one of the mission scientists we have.
Thank you very much.
You mentioned, you said one of the big outstanding mysteries is very radar bright areas. Yeah. I've seen some lurid theories involving lakes of molten tellurium and that sort of thing. Would you care to summarize the main hypotheses on what those areas could be, and to what extent Venus Express could help discriminate between those theories?
Well, I have to admit I can't summarize. I think there's an expert here, Lud Friedman, might be much more able to summarize these stuff on the highly reflective areas on the Venus surface. But I know what the status, what we believe, what it is there, and I don't think that we believe that there are lakes or something like that. And we will, as soon when we have data, we will look into it and discuss it. I don't know if Lou has some more ideas, but there are sometimes crazy ideas around on these things, and it would also take too long to go into these things from here. But I'm not an expert on the Venus surface, that I want to say. And if you look at some of the images we got from the Russian spacecraft from Venera, it doesn't look like that we have lakes or things like that.
Dick Klein, that is a really fascinating program you have, and you have terrific data that you're starting to get available here. And I wonder if you have a program to try to interest various universities to take part of this data and to work it for their own benefit and maybe your own benefit.
Yeah, thank you. What we have, and you're correct, we involve as many people as we can in these missions. As you know, the The ESA rules are that the principal investigators have basically 6 months proprietary right for the data, and then they are obliged to provide the data in a form that it can be archived and used by other scientists to ESA. So we do our best to also support this, that this is done. We did it on Venus for Mars Express to some extent already, and for Venus Express we are really after that the data are at a certain moment, and it should not be too far in the future, in our planetary science archive, which is hosted at ESAC, and then it will be available to the wide community. So, but already today, the data we have in the archive, you can access it. It's, if you go on the ESA webpage and you go to PSA, to the science archives, you will get it, and then you can really look into the data. And this is what we try to do in a form that it can be used by a lot of people, also by universities, and we really encourage this. And I think none of the PIs will even push anybody away. If we get people to work on it, they are all welcome, because we need the manpower to do it. And we try with the archive to do that much faster. And I can also promote something what we are doing together with our NASA colleagues. We are discussing next month with NASA colleagues and also representatives from other space agencies that we have some interoperability on data archives, and that we set a standard, ESA and NASA together, because we are the ones who have these missions now in orbit, that this will be then, so to say, a worldwide standard for all these planetary missions, which we already have now, but we try to really make it official and then give the opportunity to everybody who wants to use the data, that they can use it. And they should have all the information, not just that they are data, they are raw data. It should be data with calibration, all these things that you can use, and the student can use it for his work.
Oh, hi. Oh, got it on. I was wondering what extent the albedo reflection affect the thermal design of the spacecraft?
The atmospheric reflection?
Yeah.
On the... That's a good... okay, what we have done in our design, we have really taken that into account for the thermal modeling of the spacecraft. But I think for Venus still, the insolation from the sun, what we get in from the sun, is the dominating factor. We get much more heat from the sun in there. But we have taken that into account when we did our thermal design, and so far we are in very good shape. The spacecraft behaves pretty well, but even better than the predictions. All the instruments are in a very benign environment, so it works very well. But that's what you have to take into account in your thermal design, what the albedo of the planet and what you get from the sun, and then get the balance based on the orbit you fly. So this has been done by our experts, and it works.
My name is Bernd Feuermacher. Question is the following. We all know that good old Earth is warming up because of greenhouse effect. Now with Venus, we have an example where the greenhouse effect is very extreme. It's a runaway greenhouse effect. And one of the justifications to go there is that we could learn something about what happens to Earth and how the Earth develops with what mankind is doing to its atmosphere. Now the question is, I know the data that you are showing to us are brand new. They are not yet evaluated fully, but can you tell us whether there is anything from the initial results that you got now, what we could learn concerning the greenhouse effect on Earth?
I think I can say no. From the first data, as I can tell you the first data we got were from the vertex instrument for quite some time. They showed us all these wonderful images and also demonstrate how deep they can go. But you need the full data set with these. You need the profiles, the CO2, as I showed. You also see where the cloud layer, the dust, that all has to come together, plus the wind speeds, that you get a dynamic model of the atmosphere. These data, at least we got them only presented 2 weeks ago, so first of all, it's up to the PIs to really work because they have the full data set. But I'm quite sure that we will, if you will listen to talks perhaps in half a year from now or next year, I think there you will get already data sets that give you nice thermal profiles in the atmosphere and also show you at least the parameters that go into the dynamics, and where we can learn something about the energy balance in the atmosphere, which is very important to see what drives these dynamics. And I'm very optimistic from the data I just saw now recently, and I showed you a few of them today. It's okay. One has to be patient with these missions, and I hope that that the science teams continue to work hard. It's very difficult, and I want to mention that is also the funding from the funding agencies is not at the top for such a mission like Venus Express. This was a mission that came in very fast. It was a mission, you could say, a mission of opportunity. And unfortunately, one has to say that they are not always as well funded as the big cornerstone missions for the data analysis. This is not a criticism, but it shows, we have wonderful results, but one needs also manpower to really analyze these things in detail, and that takes quite some effort.
Hello, Richard Hamann, University of Stuttgart, Germany. Do you know about any other plans for further missions using the express bus system?
No, it's okay. It was a very great opportunity with Rosetta, Mars Express, and Venus Express. But if you want to use it and use it efficiently, then you have to have the sequence with no gaps in between. Yeah? So this was the big advantage. We launched Rosetta in 2004. It should have been launched in 2003, Mars Express a little bit later, and then Venus Express. So you have a sequence which is where you can use basically the same industrial team. And if you really want to use that efficiently, then you have to do it in a short sequence to make the best economy out of it. For similar missions, and if you want to be very efficient, you take the ideas and some of the designs you have used there that you basically reuse. And we also reused, or we used for Rosetta as an example. Rosetta has to live 10 years. We also looked in, so to say, spacecraft systems that have a design lifetime of 10 years, which is basically the telecom satellites. If you look at the Rosetta bus, it's really a derivative of some of the telecom satellite buses. So these things you always do, but to use it as efficiently, fast, cost-effective as we do it here, you really have to build it, in a very short interval. If there is a little gap, then you have changes in the industrial team, and you lose some of the know-how, you lose some of the efficiency, and this is unfortunately it's like this. Otherwise, it would be great if we would build a spacecraft like these in a short time sequence. On the other hand, there are also much more and exciting objects looking for us or waiting for us. ESA has Mars Express, Venus Express we have in orbit. We are building Bepi Colombo, where we go to the innermost planet, another terrestrial planet, and then there's a whole community. They want to go outside. They want to go to the gaseous giants, back to Saturn, because Titan with Huygens was such a big success. There are so much new things we learned, and so many new questions that came up, that somebody wants to go out there, and then you need a slightly different, you need another design than this one. And okay, you have to make a trade-off. It would be great if we would have this sequence of missions much more, and then it would be very cost efficient. But you have to operate these missions as well, and that also has to be taken into account. And the community has to work, analyze the data, and as I said, there are other targets waiting for us, and we have now set our sights away from the sun, again to Jupiter. Europa is there waiting for us, and again back to Titan or Saturn system.
Okay, well, I think we have learned a little bit about the latest results of Venus, and now we have learned that we have to work a lot to understand, after we unveil the planet, that now is not all of it. Now we have to work hard to analyze all these data, so we have plenty of information in our hands. And of course looking forward to results coming out of it. But I wanted now to thank the speaker again for his presentation. Thank you.